Here we go. So let's try, this is example 10.1b. So let's write it down here. This is example 10.1 and B, and we want to determine OF2. It says the geometry. When it says predict geometry, geometry is the same thing as saying predict the molecular geometry. Well, the first thing we need to do is draw a Lewis structure for OF2. Oxygen has 6 valence electrons. Fluorine has 7 valence electrons. There's 2 of those. So that's 14 plus 6. That's a total of 20 valence electrons. We're going to have our oxygen in the center, and it's going to be bound to the 2 fluorines. It's going to look something like this. So our central atom, oxygen, has 1 region of electron density, 2, 3, and 4. So it has a total of 4 regions of electron density, or 4 reds. That means that the 2 bonds in the 2 lone pairs are going to occupy the corners of a tetrahedron. And we can draw the molecular geometry in several different ways. I'm just going to draw it with the 2 fluorines in the plane of the screen like that. I'll put 1 lone pair going in the back like this, and I'll put another lone pair going out like this. So remember, molecular geometry only considers bonds, and thus my molecular geometry is bent. Okay, now if you wrote your Lewis structure like this, if you said, well, I have fluorine, then I have oxygen, like this, I have 1 lone pair in the back, and I have another one out in front like that. I say like this, so that's also bent. That's fine too. Okay, they're just different perspectives of looking at the exact same molecule. Okay, let's try the next one. This is 10.1c. It's AlCl4 minus. I'll go over this one kind of quickly. If we draw the Lewis structure of AlCl4, you'll see that it looks like this: AlCl4, and you're going to have to fill up the octets of the 4 chlorines. And if we calculate the formal charge on the aluminum, aluminum has 3 valence electrons, subtract 4 sticks and 0 dots, which gives us -1. And so the negative charge is on the aluminum. So that means our central atom has 1, 2, 3, 4 regions of electron density, doesn't it? The 4 bonds that connect the 4 chlorines. And so those are all going to occupy the 4 corners of a tetrahedron. But I have no lone pairs. So I have a central atom surrounded by 4 atoms. This is of the form AB4, okay, which we looked at earlier this evening. And so my molecular geometry is tetrahedral. Let's try the next one. I3 minus. Okay, so this is D, which is I3 minus, like that. Well, I'm going to have my iodines connected in a row like this. If I count up the total number of valence electrons, it's 7 times 3, which is 21, plus 1 for the minus charge gives you 22 electrons. I'm going to fill up the octets of the iodines on the ends. That gives me a total of 16. That means I've got 6 electrons left. I'm going to put them all in the central atom. And iodine is in the 5th period, and so it can expand its octet. That means the iodine is surrounded by 1, 2, 3, 4, 5 regions of electron density. 5 reds. That means that the bonds and lone pairs will occupy the 5 corners, so to speak, of the trigonal bipyramid. But remember, the 2 iodines are going to be at the 2 ends. And so it'll look something like this, where I have my iodine, and I'll just draw it like this. Okay, like that. And in the equatorial position, I'll have 1, 2, 3 lone pairs. The bond angle here is 180 degrees, and so my molecular geometry is linear. Let's try one more. It's C2H6. No, sorry, C2H4. Move down here, I got a little more space. C2H4. Well, remember that carbon always forms 4 bonds and hydrogen always forms 1 bond. Carbon has a total of 4 valence electrons times 2 plus 4. That gives me a total of 12 valence electrons. If I start connecting my carbons together like this, and I put, 1, 2 hydrogens like this, and 1, 2 hydrogens like this, that means I've used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. I've got 2 left. If I put them here, then this carbon has an octet, but this carbon does not have an octet. So a better option would be to share those 2 electrons. Now, this carbon has an octet, and this carbon has an octet. What did I say about regions of electron density, or what I refer to as reds? I said a single bond counts as a red, and a double bond counts as 1 red. So that means that each one of these carbons, so each carbon has 3 regions of electron density. If I have 3 regions of electron density around each carbon and there are no lone pairs, that means that this carbon here is trigonal planar, and this carbon is also trigonal planar. So both carbons have a molecular geometry, and both are trigonal planar. Well, that covers example 10.1. Let's move on from there and talk about a new kind of topic here, which is what is referred to as a dipole moment in polar molecules. Okay, so a polar molecule is nothing more than a molecule that is held together by covalent bonds, so a regular molecule, but we have an unequal sharing of electrons. What does that mean? Let's say we have a molecule like HF, okay, hydrogen fluoride. We draw its Lewis structure. Fluorine has an electronegativity value of 4.0, and hydrogen has an electronegativity value of 2.1. Means that fluorine is more electronegative than hydrogen. Therefore, fluorine is going to have more of the electron density than hydrogen, isn't it? Remember, electronegativity and electron affinity are 2 different things. Electron affinity refers to elements, whereas electronegativity is the ability of an atom to pull electron density towards itself in a bond. These 2 atoms are sharing those 2 electrons in that bond, but it's an unequal sharing. The fluorine is going to have more of the electron density, so it's got a partial negative charge. And therefore, the hydrogen is going to have a little less, and so it's going to be partially positive. We can represent those partial negatives and partial positives with an arrow that we call a dipole. Okay, this arrow represents what's called a dipole or a dipole moment. I'm not going to ask you to calculate a dipole moment. Okay? A dipole moment is this variable here, mu, which is charge times the distance between the charges. And the units that we use to calculate dipole moment, it says here 1D. The big D stands for debye. Okay, that's the name of the unit, which is equal to 3.36 times 10 to the negative 30 coulombs times meters. Now, again, I'm not going to ask you to calculate this, so I'll even put that in here. Let's just write will not ask to calculate. I'm not going to ask you to do that. However, there's one thing I want you to understand. Larger mu equals larger dipole. Now, if you're wondering, what do you mean by larger dipole? Okay, well, let's look at, a different molecule than HF. Very well did it. Okay, what if I have, I don't know, HCl? Well, there's still a dipole because chlorine is more electronegative than hydrogen, but it has an electronegativity value of around 3. Okay, so we'll put down here chlorine, more like it's close to 3. So that means there's going to be an unequal sharing, but the dipole is not going to be as strong. And so the mu, or the dipole moment here, would be less. Okay, so the mu here would be smaller than the mu or the dipole moment between H and F. Okay, that's all it really means. Now, that means that the molecule is polar. So if there's an unequal distribution of electrons throughout the molecule, that's called a polar molecule. Here, this is called an electrostatic potential map, an EPM. And the red means electron density. So you can see that the molecule has more electron density. Maybe I should use a different color. There's more electron density over here than it does over here. Well, what do we mean by a polar molecule? What can a polar molecule do? Well, one of the ways that you can determine whether a molecule is polar or not is by the way it behaves in a magnetic field. If you have a bunch of polar molecules in a solution, let's say, and you have no external magnetic field applied to them, what you're going to see is they're going to kind of line up or align themselves randomly to some degree. Now you can see that the delta pluses and the delta minuses are going to be close to each other because opposites attract. But you see, you kind of have some over here, and then you have some here, and here it's kind of lined up. This one, these two are kind of lined up. Right? They're kind of randomized to some degree, even though the dipoles are going to line up so that the delta pluses and the delta minuses line up. Whereas if you apply a magnetic field to a sample of polar molecules, what you're going to see is that they're going to align with that magnetic field. You see how we have the positive side of the magnetic field here and the negative side here? Well, look at the way that all of these molecules are aligning themselves. They're kind of aligning themselves such that the delta pluses are all pointing towards the delta negative, or the negative part of the magnetic field, and the negative parts are all kind of lined up towards the positive end. So that's one way that polar molecules distinguish themselves from nonpolar molecules, is their behavior in a magnetic field. Now, before I even go on, you're like, okay, cool. When am I going to turn a magnet onto a molecule? When am I going to, hit a molecule with a magnet and go, "Ooh, look at that molecule move"? Okay, what's the point? The point is this: in order for you to understand some physical properties, like melting points and boiling points, really well, you have to understand polarity. Okay? You really have to understand when a molecule is polar and when it isn't. So, just like a lot of things in chemistry, it's going to kind of, we're going to kind of build off of this polarity concept. Well, let's look at some bond moments. And when it says bond moments, it means bond dipole moments. Dipole moments and resultant dipole moments in ammonia and nitrogen trifluoride. Let me draw these molecules a little bit bigger, and we can actually hang out on this slide for a little bit. So I'm going to try to draw their molecules the same way they did. Remember, both of these molecules have 3 regions of electron density. They both have 3 atoms in one lone pair, so their molecular geometries are both going to be trigonal pyramidal, right? Whether it's ammonia or nitrogen trifluoride, they're both trigonal pyramidal. I'll do my best to draw these like this. What if we look at the electronegativities of nitrogen, hydrogen, and fluorine? Well, if we look at the electronegativities of these elements, hydrogen is around 2.1, nitrogen is around 3, and fluorine is around 4.0. So if I look at the types of bonds in ammonia, they're nitrogen-hydrogen bonds. Since nitrogen is more electronegative, the dipole, we point the arrow towards the more electronegative element. Okay? You see these 3 vectors? What are they doing? They're all heading up towards the top of that trigonal pyramid. They're all going to kind of like run into each other, and then you get what's called a resultant or a net dipole moment. So basically, you have to be able to add those 3 vectors in your mind. Here's a trigonal pyramid. I've left out the lone pair. Okay, I've just taken it out. But look, if I have something going up in this direction, something else going up in this direction, and something else going up in this direction, when the three things collide at the top, boom, they're going to have a resultant net dipole that's going to go up like this. Okay, it's going to be pointing straight up. And so my net dipole is going to be pointing up like this for ammonia. Okay, that's going to be my net dipole. I'll use the smaller pen just so I don't screw it up. There we go. So this is the resultant or net dipole. So we say this is a polar molecule because it has a net dipole. If I look at nitrogen trifluoride, it's very different, isn't it? Because if I can look at the dipole here, fluorine is more electronegative than nitrogen. So I draw the three dipoles going in this direction. That means that my net dipole is going to be pulling down like this. You're like, well, what do you mean? Well, think about it. If they're all pulling down in equal and opposite directions, overall, the net effect is going to be to have a resultant dipole going in this direction. So this will be my net dipole. Okay. Notice also that I left out the dipole moment on the lone pair, but the lone pair does have a bit of a dipole moment. So on the nitrogen dipole, or sorry, the nitrogen lone pair dipole is going to be going towards the lone pair because they're not shared. Oops, color consistent here. Anyhow, give me a thumbs up if you see, at least see, the net dipole and where it comes from. Because it's very important that you can add these vectors in your mind. Okay, cool. Well, if we look at the electrostatic potential map, which is shown here, these are two electrostatic potential maps, which again show you where the electron density is in the molecule, right? When we look at a molecule, if we could actually shrink ourselves down to the atomic level and look at the molecule, we're not going to see the letter F and we're not going to see little dots or anything like that. But maybe we would see where more electron density is. And the red means electron density. So in the ammonia molecule, since the dipole is going in this direction, you can see that virtually all of the electron density is up here on that lone pair, right? Going up towards the top. Whereas in the nitrogen trifluoride, not only do you have electron density down by the fluorines because it's the most electronegative element on the periodic table, but you also have some electron density on that lone pair as well. But again, the main take-home from this take-home message from this slide is that ammonia's net dipole is going up in this direction, and the net dipole for nitrogen trifluoride is going in the opposite direction. Why? Because of the difference in electronegativity between hydrogen and fluorine. Here are some dipole moments of some polar molecules. Again, I'm not going to get you to calculate dipole moments, but what did I say? The higher the dipole moment, the bigger this number, the more polar the molecule. For example, HF, hydrogen fluoride, is very polar. If I look at HI, so as I go down from fluorine to chlorine to bromine to iodine, you see that I have something that's less polar, right? The polarity decreases. Why? Because we see that in the halogens, going from fluorine to chlorine to bromine to iodine, what happens going this way? Electronegativity decreases. And so the bond becomes less and less polar. If I look at the dipole moment for water, I can see that water is a very polar molecule, right? It's comparable in its dipole moment to hydrogen fluoride. And then you see H2S has the same molecular geometry as water, bent, but the dipole moment is less. Why? Because sulfur is not as electronegative as oxygen, and therefore the dipoles simply aren't as strong. All right, again, I'm not going to ask you to measure dipole moments, but you should know that the greater the dipole moment, the more polar the molecule. Well, let's look at another example. I'm not going to ask you anything about microwave ovens, so let's just move on. It says, predict whether each of the following molecules has a dipole moment. Let's start with the first one, BrCl. If we were to draw a Lewis structure for BrCl, since they're both halogens, it's going to look something like this, isn't it? Now, even if you don't have the electronegativity values memorized, no big deal. Because we know, as I said on the last slide, that electronegativity decreases as we go down a group, right? En decreases. So that means that chlorine is more electronegative than bromine. That means it's going to pull more of the electron density towards itself. So this will be a polar molecule. The answer is yes. What if we have BF3, boron trifluoride? We looked at boron trifluoride this evening, and we saw that it's trigonal planar, isn't it? It even tells us that. So we're going to have those three fluorines right over here like this. Now look, again, you don't have to have the electronegativity values memorized. Fluorine is 4.0. Boron is around 2.0. Again, you still don't have to have them memorized because fluorine is the most electronegative element in the periodic table, isn't it? Therefore, there's going to be polar bonds in this molecule, aren't there? There's going to be a polar bond here. There's going to be a polar bond here. And there's also going to be a polar bond here. You got three beautiful polar bonds in boron trifluoride. My question to you is, does this molecule have a dipole moment? Yes or no? Does this molecule have a dipole moment? Bruce says no. He's absolutely correct. No dipole moment. No dipole moment because the dipoles cancel. Right? Think about it. They're all pulling in equal and opposite directions of an equilateral triangle. So they all cancel each other out. Well, let's look at one more example. I'll go over this one a little bit quicker. It's CH2Cl2. It's called dichloromethane. I'll give you a second to think about it while I move some things around here. It tells us that CH2Cl2 is tetrahedral, so it's going to look something like this. I'm going to have my carbon, 2 bonds to hydrogen, bond to a chlorine, another chlorine. I'm going to include my lone pairs. If I look at the electronegativities of carbon, 2.5, hydrogen is 2.1, and chlorine is around 3-ish. That means we're going to have some polar bonds in here, aren't we? Well, even though the difference between carbon and hydrogen is really small, there's going to be a little dipole, right, going towards the carbon because it's more electronegative. Between the carbon and the chlorine, though, there's going to be a bigger dipole, isn't there? Now, what's the net dipole going to be, the resultant dipole? I can tell you what it's going to be. It's going to look like this. It's going to be pointing in this direction. Now, how did I know that? Because take a new tetrahedron here. Maybe I'll get a couple of different atoms here. Give me 1 second. So I'll use green to represent the chlorines, I guess. Here's what I had drawn. So I'm trying to hold it so you can see all the bonds. If I have a dipole going this way, they're going to converge. And then I have 2 dipoles going out this way. If I add up all 4 of those, they're going to equal a dipole that's going out like this from my molecule, going out like that. Imagine it another way. If you have somebody pulling here, somebody pulling here, somebody pushing here, and somebody pushing here, it's going to force the molecule in this direction. Okay, overall, it's going to head in this direction. And that's how you add up the dipoles in your mind to determine the resultant dipole of the molecule. All right, give me a thumbs up if that helps. And if you can determine, or if you think you can determine when a molecule is polar or when it's not. Obviously, it's one of those things that requires practice. You know, don't ever think, oh, I didn't get it in the first 5 minutes. That's impossible, okay? It takes a while to, you know, get a handle on when a molecule is polar or not. Well, let's switch to something completely different here for a minute. Yeah, let's talk about a bond. Let's talk about the most simple bond we can have in chemistry. Let's talk about two hydrogen atoms. Okay, if I have a hydrogen atom, by now you know that hydrogen has an electron configuration of 1. It's got 1 valence electron. You know that hydrogen can form an H2 molecule, right? H2 molecule like that. Well, if I have two hydrogen atoms and they're separated, there's going to be no interaction between those. We say that the potential energy of each of those hydrogens is 0 because neither of them are bound to anything. Well, what happens is those hydrogen atoms get closer and closer to each other. So here they are a little bit closer and closer. What's going to happen is that the electron of one hydrogen is going to be attracted to the nucleus of the other hydrogen, and the other electron from the other hydrogen is going to start being attracted to the other nucleus like this. And what's going to happen is that those two atoms are going to get to a certain distance from each other where attractive forces are going to be maximized and the repulsive forces of the two electrons and the two nuclei are going to be minimized. So again, what did I say? Once we get to here, we find a well in terms of the potential energy. It gets as low as it can. And that distance between the two nuclei is the bond length between the two hydrogen atoms. And again, the reason why they bond to form H2 like this is because the attractive forces are maximized between the electrons in the nuclei, and the repulsive forces are minimized. All right. Well, let's think a little bit more about this bond. If that one electron is in an s orbital, what's the shape of an s orbital? Right? An s orbital is simply a sphere. So that means you've got a sphere with an unpaired electron and another sphere with an unpaired electron. They're going to come together, they're going to overlap, and they're going to share those two electrons. Now, before we represented them as something, you know, one electron going up and one electron going down to represent the two shared electrons have opposite spin. All right. Well, that makes sense for H2. What about methane? Does that make sense? You know, again, it really makes sense here because I get two spheres coming together and I have this linear shape like that. Well, what about something like methane? CH4. We talked about methane this evening, right? We said that methane's Lewis structure looks like this. Okay, that's the Lewis structure of methane. And then we said that its molecular geometry was tetrahedral. And it looked like this, where all 4 hydrogens took up the 4 corners of a tetrahedron. And those beautiful bond angles were all the same. They were all 109.5 degrees. Does this make sense based off of the electron configuration of carbon? If you're like, what do you mean by that? Well, we think about the carbon as having 4 unpaired electrons, and we think of the hydrogen as having 1 unpaired electron because carbon is from group 4A, and hydrogen is from group 1A. Well, the hydrogen makes sense because its one electron is in a 1s1, or it's in an s orbital, isn't it? Right? It's just a sphere with an unpaired electron in it, wherever you want to put it. You know, I put it here. It doesn't matter. But what about carbon? That's a little bit trickier, isn't it? You're like, what do you mean by it's trickier? Follow me along here. Carbon has an electron geometry, an electron configuration of helium, 2s2, 2p4. We know that an s orbital is a sphere, and a p orbital looks like something like that. Okay, a peanut, right, or a dumbbell. Did I say 2p4 when I meant 2p2? Anyhow, there we go. So if we draw the orbital diagram, we have s, and we have 1, 2, 3 p orbitals. We have 1, 2 electrons in here, and then we have 1, 2 electrons in the p orbitals. What the hell? How in the heck could carbon have 4 hydrogens that are going to occupy the 4 corners of a tetrahedron? That doesn't make any sense. If you're like, why doesn't it make any sense, Mr. Dion? Well, I can give you 2 reasons. Number 1, it doesn't have 4 unpaired electrons according to this. It's got 2 unpaired electrons and 2 electrons that are paired up, so that's no good. Not only that, the 2 s electrons are in a freaking sphere like that, and they're paired up, and then I've got 2 electrons in 2 p orbitals. If I draw what the heck I could even get from that, I'd have a carbon atom. Let me just try to fudge this here. I'd have a carbon atom with 2 p orbitals, you know, and I'd have an unpaired electron in each, and then I'd have a sphere with 2 electrons. Like, that's not going to give me the 4 corners of a tetrahedron. That's impossible. You'd be absolutely right. So there's some kind of disconnect between our Lewis structure of our carbon atom and our electron configuration, isn't there? You can see that that will not give you a tetrahedron. That would, you know, you'd be able to form a bond here and a bond here, and it would look, you know, it wouldn't look anything like a tetrahedron, neither here nor there. What it would look like. The answer is that we're going to make a brand new type of orbital. You've learned about s orbitals, you've learned about p orbitals. We looked at pictures of d orbitals and f orbitals, but tonight we're going to learn about brand new orbitals. How do I explain the tetrahedral geometry of methane? This is how I'm going to do it. What we're going to do is we're going to mix some orbitals in a blender, not literally, but figuratively. I'm going to take one of these electrons and I'm going to move it into a p orbital, because that way I'd have 4 unpaired electrons. But if I was to just take, you know, 1 electron from there, right, and put 3 electrons in here, okay, that solves part of my problem, because now I've got 4 unpaired electrons and I want to form 4 bonds. I want to have 4 unpaired electrons like my Lewis structure, but there's still a problem because they're in 2 different types of orbitals, and I need 4 orbitals that are going to be spread out equally. So I mix them up this way. I mix all the orbitals together so that I have 4 orbitals that are all perfectly identical. What are they made up of? They're made up of 1 s orbital and 1, 2, 3 types of p orbitals. I give the name of these 4 orbitals, I call them sp3 orbitals. And I'm going to have 1, 2, 3, 4 electrons. So I've got 4 unpaired electrons. Beautiful. That's just my Lewis structure. And they're all in orbitals that are identical. And we call this a hybrid orbital, because what's a hybrid? Right? If you have a hybrid car, it runs on gas and electricity. Okay. Well, a hybrid orbital, in this case, happens to be made of 1 s orbital and 3 p orbitals. Okay. How do you draw this new orbital, Mr. Dion? Well, let me show you. If you look at the book, an sp3 orbital, they'll have a big lobe on one side and then they'll have a little lobe on the other. Well, Mr. Dion's way of doing it is just going to be draw one big lobe. Okay. And you know how you're going to know it's an sp3? Let me tell you. I'm going to label it. All right, sp3. So that means you've got 4 hybrid orbitals. Let's go one further. So now I'm going to have a carbon atom. I'll draw it over here. It's going to be surrounded by 1, 2, 3, and I'm drawing a dash here to show that this sp3 hybrid orbital is going in the back. And 4, I'll try my best to show this one coming out in the front. Okay, Mr. Dion is not an artiste. Okay, so now I've got 4 orbitals, 4 hybrid orbitals that are all going to spread as far apart from each other as possible. They're going to adopt a tetrahedral geometry. Each one of them has 1 unpaired electron. Let me show you. 1, 2, 3, 4. Bonds result from orbital overlap, don't they? If you go back to my slide deck, it showed you how a bond was formed by the overlap of orbitals. So what we're going to do is, since we've got 4 hydrogens, and each hydrogen has a 1s orbital with 1 electron, look, I'm going to get a 1s orbital from 1 hydrogen here, overlapping. It's got 1 electron. So look, I got 2 electrons shared in overlapping orbitals, right? A 1s orbital and an sp3 orbital. That's a bond, people. That is a beautiful, beautiful bond. We're going to do it again here with another hydrogen. It's a 1s orbital. Get another electron. Opposite spin. I get another hydrogen atom here. Again, Mr. Dion is not an artist. And I get another one here. Here's another electron. It's the reason I'm writing H is just so you know it's a hydrogen. And the reason I'm putting 1s, so you know it's a 1s. I'm giving you all kinds of beautiful information here. This is called hybridization. All right, if you go back to the first page on our slide deck, what was the title? It says molecular geometry and hybridization of atomic orbitals. So we're taking atomic orbitals, s orbitals, and p orbitals, and we're mixing them together, and we're making hybrid orbitals. And that explains why carbon can adopt a tetrahedral molecular geometry. We have to hybridize the orbitals in order to explain this. Hybridization is the mixing of 2 or more atomic orbitals to form a brand new set of hybrid orbitals. The way that we form hybrid orbitals is that we're going to mix at least 2 non-equivalent atomic orbitals, like an s and a p, or an s and a p and a d, okay? Hybrid orbitals have a very different shape from the original atomic orbitals that we looked at. What were atomic orbitals? Those were the s, p, d, and f orbitals. The number of hybrid orbitals is equal to the number of pure atomic orbitals used in the hybridization process. For example, what did I just show you? We had 1s in the sp3 hybrid orbitals that came from 1s orbital and 3 p orbitals, or p orbitals, and there's 1, 2, 3 of them. So how many sp3 orbitals did we get? We got 4 sp3 orbitals, right? Covalent bonds are formed by the overlap of hybrid orbitals with atomic orbitals, or hybrid orbitals with other hybrid orbitals. That's it, my friends. We go back to our hydrogen molecule, right? We started out with the right. If you look at an electrostatic potential map, where's most of the electron density? In the center, where the electrons are shared. And that's why when I drew a hydrogen 1s orbital with 1 electron, we show that the other electron is being shared in the center. This is another hydrogen 1s orbital. Like that. How did I make that sp3 hybrid orbital that I showed you? I put all of these in a blender, right? I took 1s in 3 different p orbitals. So an sp3 orbital, hybrid orbital, is 25% s character, and it's got 75% p character. See, the shape is mostly like a peanut or a propeller. Again, in the book, their sp3 orbitals will look like this, okay? Mr. Dion's are going to just look like this. Why do I leave the little part out here? Because it's just a pain in the neck to draw it. Nothing more than that. Do you have to draw it? No. Okay. There you go.